Okay, Assalamualaikum and a good morning. So today we'll continue the lectures after I think the Monday slot was no, you had your first test. I hope everyone is fine with the first test. So I'll be marking it soon because the deadline is supposed to be this coming Sunday. Right. So today I will be again using the whiteboard because I have not typed all the notes as yet. So please bear with me. So today we are remember when we had the question, the unanswered questions sometime at the end of the lectures for thermodynamics. One of the things that we wanted to know is to be able to see some microscopic understanding of the second law. Well, initially a microscopic understanding of entropy, and then of course we have the second law that states essentially your entropy always increases. So today we're going to cover essentially just that. So today we are having, I've not connected my tab. Just give me a minute. If this works. Okay, I have to close my application first and then restart. Okay, hopefully now, let me see. It's not working at the moment. Try to do this again. Okay, so that should. Okay, can you give me a minute? So can you see my writing?
Yes.
Okay, great. So today, as I said, we are going to look into second law of thermodynamics from the context of the the microscopic picture of it. So the entropy itself, we have already seen entropy in terms of this formula, where W is essentially the number of accessible states for the system. Accessible states. Okay. And this is essentially given that you know W, then you can calculate out your entropy. But let's invert this formula, and we'll try to talk about W, which is the number of accessible states, but now written in terms of entropy. Okay, so in other words, given entropy, then one should be able to the number of accessible states. So let's do that. And so in other words, here in this particular sort of context, your S is supposed to be given. So given, oops, why is it becomes Q? Given that your S is of the system, and you know that it relates to the energy. Okay? It's related, it's a function of the energy. So suppose we consider system A. So let me just put it there, system A, and then the energy will be UA. Okay. So in other words, your S will be a function of UA. Okay. So now if we understand the second law, you know that how should I say this? The entropy will hit the maximum. Okay, recall entropy hits maximum when it is in equilibrium. Okay, so this we know from the past lecture also. Okay, let me go down. Maybe I use the mouse. Okay. So so meaning we will consider the case where when this happens, this is precisely at some particular energy. So, and this happens at say UA star. Okay, so the thing that hits the maximum is the entropy, not the energy. Okay, so energy UA star is the essentially the energy for which when entropy is maximum. Okay, so that's all it is. Okay, so now what we want to do is to be able to expand this function. So expand function as Taylor series. And usually we need to define about which point. So we about where it is the entropy is the maximum. So that means about UA star. So you remember what Taylor series is. So let me just write it down here. For some reason I'm getting my okay. So S UA So the zeroth order term will be at will be the entropy evaluated at UA star. So that is UA star for the zeroth order term. First order term, then you have this expansion. So remember here, this is your variable here. So U is minus the point over which is expanded on. Okay, and then you take the derivative, the first order derivative with respect to UA, and then this is evaluated at UA equals to UA star. So I hope you still remember how we expand a particular function in terms of Taylor series, where you have this kind of summation x minus x naught to the n, or n factorial, and then you have dn, df, dxn evaluated at x naught. Okay, so it's just using that formula, and we can go to second order at this. Okay, because we want to prove the idea of entropy increases. Okay, so we need the second order one, and then this will be multiplied with so this is squared, sorry, this will be multiplied with the second order derivative, at UA star, and then you can continue for higher order terms, but we will stop at that at the moment. Okay, so let's see what do we have. Here we have the first order term is essentially going to be 0. So at maximum s, okay, your derivative is actually 0. So that's why we need to keep to the second order term. And the second order term, so let's, oops, what did I do? Okay, I know how it works. Okay. So second order term involves the second derivative, so I'm going to write second derivative in terms of these dashes. S double dash equals to the second derivative at U in star, and for this to be a maximum, okay, remember this is maximum here, so this has to be less than 0. Okay, so now what we're going to do, the fact that we have expanded the entropy as a Taylor series with this, about the maximum not maximum energy for which the entropy is maximum, and then we plug back to this. So we're going to plug this thing back into this. Okay, so let's do that. Oops. Okay, further up. Okay, that should be good. Right, so we'll plug that power series inside your WA, sorry. So then you remember that it's inside the exponential there. S U A star over KB, this is the 0 order term, and then you have the first order term to be 0, so that is just e to the power 0, and that's just 1. And the second order term will give you this. UA minus UA star square times the second order derivative S double dash divided by your Boltzmann constant. Okay. So over here, what's happened now, you can actually see how the distribution of the states in a way, because what you see over here, this is just a constant. Remember, this is just a particle value of the entropy here, and divided by the Boltzmann constant. So the one that varies with respect to the variable here, okay, is this part of the exponential, and this is essentially a Gaussian function. Okay. And you know, Gaussian function, we have introduced this in the lectures of probability and statistics. So it will have a peak. So the peak is at UA star, and it will have some kind of width. Okay, the width, or I should say the standard deviation, is given by, let me write the symbol first, delta UA, where delta UA is essentially this thing, well, the reciprocal thing. So minus let me check with the book. Why is it? Sorry about this. Just to double confirm. Yeah. So there's minus KB on S double dash. Now, why is it a minus? You have to remember that your S double dash is essentially negative. Okay, so then this negative cancels off with this negative, and then you have a positive wave. Okay, so now we made some notes about this. So note, first note, here essentially the formalism of statistical mechanics together with what is known about the entropy it predicts fluctuations in energy about UA star. Okay, and the magnitude of fluctuation is given by about, sorry, Control Z of magnitude delta U. Okay. So Now, what else do we know about this? Essentially, to state that when is it maximum? It's maximum. The entropy is maximum when it reaches this particular energy UA star, and remember, when is entropy is the maximum is entropy is maximum when it reaches equilibrium. Okay, so here essentially what you have, the equilibrium state how should I say, stays at maximum of the entropy but even though you have an equilibrium state, meaning most of the properties do not change, the fact that you have these fluctuations, that means it how should I, accommodates, okay, it accommodates energy fluctuations about U is the fluctuations. Now this we have to understand in the context where equilibrium state as no the macroscopic variables at that particular point in that equilibrium state, you're not supposed to see any change. Okay, so this is something like a bit of it's not a conflict at the moment, but it does sounds conflicting. Okay, you equilibrium is a state where your thermodynamical variables do not change, but yet you entertain possible fluctuations. Okay, so this is the thing that I wanted to stress. Okay. And how should we understand this? Is we look at the probability of the states when it reaches this what you call equilibrium state where entropy is maximum. So for that we need another oops, I want to do that. I want to just push this thing out. So consider now the number of states, number of accessible states, so these are in this particular case we will write as W, but now your W is a function of UA. Okay, and we would like in a way because entropy is related to this accessible states, you would like that number to be maximum at UA star. Okay, so this will be actually maximum at WUA star. Or in other words, most of the states are how should I say are around UA star. Okay. So can we define the probability of this? So let's recall what we had earlier about classical and statistical probability So in this particular case, you have to consider the relative frequency of a particular energy state. Okay, so here I'm going to write in terms of, well, okay, first of all, you have the classical probability. Let me just point that thing out. Classical probability, which says that all states for particular all, all states for particular energy is equally probable. But then you have your energy to be as a parameter. Okay? So that will apply to the idea of relative frequency. So that means we need a kind of relative frequency idea here, because you have this possibility of having different energies. Relative frequency. So in other words, the probability will be something like this. Probability of UA will be the number of UA states divided by the number, sorry, too far away, all the possible energy states for the system. Okay. But with WUA star being the maximum, one consider then this will also be the maximum. Okay, so this is also right. So if you take the ratios, okay, the ratio of probabilities, say PUA, which is not necessarily at the maximum entropy or at the equilibrium state, divided by probability of UA star, where it reaches the equilibrium state, then using the earlier, remember that these are the definition, okay? So these are the definition of your probability here. So, and the way it's being done over here, you can see that this is a common factor because this is being summed. Okay, so this will drops off. So the one that's going to be relevant here is the number of accessible states at the energy UA and the number of accessible states at the energy UA star. Okay, and we have already the, oops, I want to go up. Where is it? We already have this. Okay, and again for this, you see that this is a constant term. Are you seeing my cursor, by the way? Somebody? Can you move around? Okay, good. So this is constant term. So remember, previously down below we need your ratio between this WUA and WUA star. So what's left? So this will cancel out because it's common term for both numerator and denominator. So the ones that's going to be left is this. And for WUA star, this is going to be 0. Okay. Excuse me. Okay, and let me go down below then. So this will now become taking into consideration all the things that I mentioned just now. So this will be exponential minus UA minus UA star square divided by 2 delta UA squared. Okay. So, okay, what's the point of all this? The point of all this is to show that if, for example, you started off with a system with certain amount of energy, then it goes to equilibrium state, what's the probability of that system going back? Okay, so this is essentially the thing that we want to do. So let's work out some numerical example. Okay, so example here, system A has energy UA star plus say 20 delta UA. So in other words, this is a deviation from the equilibrium state. Okay, so let's look at what's the probability of that. So if you look at that, then the ratio with respect to the probability of the equilibrium state, UA star, this is given in terms of this exponential, so E minus UA star, okay, UA is now that, UA star plus 20 delta UA minus UA star squared, whole thing squared, divided by 2 delta UA. So this cancels off. Okay, so you're left with this thing square, which is a 400 delta UA squared, and that gives you sorry. I think, let me think about this. Let me check with the book. Did I do something wrong? Oh, okay. I've forgotten about the square here. Okay, remember there's a square there. So that's okay, that settles that. So in other words, what you have is essentially this gives me e to power of 400 divided by 2, your delta UA squared cancels off, so you get this very small number. So in other words, this probability is very much less than this probability. Okay. So just let's continue a little bit with this kind of numerical demonstration. And so if you consider a system to sample state every, say, 10 minus 50 seconds, which is almost instantaneous kind of thing. So the fluctuations that one should think of over here are expected around every 10 minus 50 multiplied by that factor of exponential minus 200. And that is, if one works this out numerically, this is about 10 to the 38 second, which is greater than the age of the universe. So you can see how, so this is very, it's not impossible, but it's very improbable. Okay, so to think of the system goes into equilibrium state and then to return back to its say to some other states which is different from the equilibrium, okay, is very improbable in that sense. Okay, so let me just conclude by saying that practically one does not see fluctuations after reaching the equilibrium. Does not see. You think faster than you write. Okay. So that answers the previous question about saying there's some kind of contradiction, saying when you have reached the equilibrium, your physical system will no longer have these visible changes in the physical properties, but yet you allow fluctuations to come in. But this numerical example says that, okay, you will probably if you want to see those fluctuations, you probably have to wait so long that you don't really see those fluctuations anyway. Okay, so that's the main idea. Okay, so let's consider now, say, two systems. Consider lagging now. Consider two subsystems, excuse me, A and B, and let the entropy is written in this way: SA plus SB. Okay, for that matter, then you can see that the entropy of the B subsystem is essentially equals to the total entropy minus the entropy of subsystem A. Okay, and what we're going to do is to connect back with some thermodynamical variables that we have seen before. So one of the formula that we had earlier was to look at the derivative of your entropy. So let me just write it down. Hopefully you can look it up back again from the older notes. Okay, I know I'm lagging in terms of the notes, but I think for the thermodynamics, all notes are already up on the Putra Blast. Okay, So the derivative of the entropy with respect to the energy, the internal energy, is given in terms of your, what should I say, is given in terms of the inverse temperature. And remember that over here, I should have written it down. Okay, maybe I'll do it here. So here, this part is going to be another function which is related in this way. So the derivative of s, the s or dua, you differentiate that as well, okay? So that will give you 1 over dA, okay, from the previous thing. But you also need to differentiate that, but that is just s minus sa, and then because of that, because of this negative sign, you have minus 1 over dB. Okay, so that is the derivative, the first order derivative. Then you have your second order derivative that one can consider. So s double dash then essentially you need to differentiate this another time with respect to UA. So let me just write this thing down first. dTA inverse dUA plus let me just check. It's a bit strange, I might have a sign wrong here, but I will confirm back with my typewritten notes. So I'm just a bit confused a bit. This is dB inverse dUB. Okay. The plus is because I'm using UB. Okay. So if you so I need that anyway. So so instead of, no, you're supposed to differentiate with respect to UA, but I'm differentiating here using UB, so there's a negative sign inside here compared to the derivative of UA. So that negative and with this negative, that gives you a plus. Okay. And if you take the differentiation of inverse TA here, that will give you minus 1 on TA squared. dTA over dUA. So this is just chain rule. And then the same thing happens for the B part. dTB dUB. Now the reason why I'm using, instead of just the variable UA, I'm using UB as well, because we want to relate it with something else. You recall, let me just put aside here, recall your heat capacity at constant volume is given by du dt. Okay, so I'm going to substitute this into here. Okay, and this will give you remember, this is going to be evaluated at the equilibrium state. Okay, so this will have a common there's a few steps in between, I suppose. There will be a common temperature depth when it reaches the equilibrium state, and this dt over du is 1 over Ca, and this one is 1 over C. Okay. So in other words, what we have seen is we can relate. Remember, your S double dash is with respect to fluctuations, okay, and one can relate this with the heat capacities of two subsystems. Okay, so what happens is when you consider say two bodies in equilibrium, normally there'll be one subsystem where for example, as a heat bath, for example, okay, your heat capacity is very big compared to the other subsystem which you are interested in, for example. Okay, so usually what happens over here, so let me just consider CB, say this, you can think of kind of heat bath, for example, then this heat capacity is much bigger than Ca, then your S double dash becomes approximately equals to minus 1 on T squared, 1 on Ca. Okay, that will actually give you the fluctuations. Remember, your S double dash is related to the fluctuations, so that will actually give you the fluctuations to be related to the temperature squared multiplied with the heat capacity of the subsystem. Okay, so one could actually look at this sort of experimentally. Okay. The other thing that one can look experimentally is also the following. Heat capacity is proportional to the number of particles. Okay. So so what happens over here, then you'll find that, okay, so here then, for example, Ca is proportional to, say, N, okay, then your delta UA, that means I'm taking the square root of that, UA is now proportional to N to the half, and UA star, where you want to compare the fluctuations with respect to the equilibrium condition of the energy, UA star is proportional to N, and then essentially you can take the ratio between the two, delta UA divided by UA star, then this is roughly proportional to the N minus a half. So here the fluctuations are being related to the number of particles, but the number of particles are usually enormous. So as N increases, then you'll find that your fluctuations, you will probably never see them. Okay. All right. What else? Okay, the way we have actually argued so far, so let me just go back to the beginning, is to use the entropy. So now let's just go back in the beginning. Remember, entropy has its own properties, but it's supposed to be explained in terms of the number of accessible quantum states, for example. Okay, so we would like to actually also do that. So let us now relate back to the number of accessible states. Why is it not going up? Oh, I'm not used to this. Come on. Okay. So let's consider again your subsystem, but now we are thinking in terms of your number of accessible states. Consider again subsystems A and B. Such that the total energy is constant, and then let WA, UA, let me check, I'm just afraid that I get disconnected. Let WAUA to be number of states of energy in this interval, UA plus DU, and WB is the same thing, number of states, energy in UB plus DU. So the other assumption one needs is that the U here is considered very much less than UA in a way to make your such that statistical probability is well defined. So okay, so what we want to do is now let's suppose consider initially the two systems are separate and they are thermally isolated from the rest of the universe. Okay, so initial number of states with A isolated from B will be just, okay, so to show that this initial, there will be a superscript I there, so it corresponds to the initial number of states. It will be just given by WUAI, the initial energy of A, multiplied by the number of states for system B, because they are considered independent of each other at the initial energy UBI. Okay. So, and then after that, we put them in thermal contact, put A and B in thermal contact, then the number of sensible states will now be different. So let's suppose it comes to the final condition of the say in the equilibrium, for example. So this becomes sum of WA UA, but now the fact that UA might change, okay, because there are exchange energy with the system B. So but you need to make sure the total energy is constant. Somewhere I've written that, okay, UT is constant there. So I can write it in this particular form. So WB now becomes a function of UT minus UE. Okay, and finally, when it reaches equilibrium, one should have the following: WA UA star WB UT minus UA star. This is when it is in equilibrium. This must be the biggest, remember? So this has to be much bigger than WI. Okay. Where WI is that, okay? So if one looks at the relative frequency, okay, so recall now, let's say how should I do this? So let's do the relative frequency first. So relative So, for example, for the initial state, and divide by WA at equilibrium, and since this is going to be very much larger than that, this is going to be very small. Okay. And if we look at the case of the previous numerical example, this is probably of the order, say, E minus 400 kind of thing. So then essentially this tells us, okay, this is going to be negligible. And remember what this is, you have reached the equilibrium, going back to the initial state, it's not going to be possible. Okay, so that is essentially that. Let me see what else is there. Okay, some numerical examples again. So let's put some factors in. Remember that we already shown you how to make connection with the fluctuations with heat capacity. So now we try to do some numerical example. And then we put some temperature here. Suppose A is at 300 0.2 Kelvin and B is at 300 Kelvin, and it goes to equilibrium, will reach the same temperature, which is this should be about 300.1. Okay, and let's just say that A and B has the same heat capacity. Uh, 1 joule per Kelvin, an easy number to calculate. So the change in entropy now, or the fluctuations, can now be written as C log of 300.1 times 300.1. This is the system A will reach the same temperature there, system B is same temperature there. Okay, remember that this is the you're supposed to relate with the log of the number of accessible states, and now it's written in terms of with respect to the temperature. And then system A is 300.2 and system B is 300, and this is about 1.1 times 10 minus 7 joule per Kelvin. Now, you might say, okay, this is nothing impressive about this, but let's rewrite this. Your delta S in terms of the number of accessible states. And this should be equals to that according to the thermodynamical formula. So that would tell us what? That the log of Wf over Wi, okay, which is just coming from there, is equals to 1.1 times 10 minus 7 divided by Kb, which is 1.38 times 10 minus 23, and that is enormous. 8 times 10 to the power 15. And then remember that it's a log. Okay, so if you take the exponential to get rid of the log, the difference, the ratio of the difference of the number of states in the final, well, in the equilibrium state in this case, okay, over the number of accessible states at the initial configuration is exponential of this number. And that's enormous. Enormous. Pull this up. Increase in number of accessible states, which is what? Exponential of 8 times 10 to the 15. Now, one could, okay, let's maybe perhaps what we can try to experiment around is to make this difference in temperature to be smaller and smaller. Okay, so let's try to do that. This is also come on. Slowly, so I cannot respond too fast. Okay, so let's repeat the calculation. Repeat for the case where the difference in temperature between A and B is much smaller. Just now is what? 0.2, right? 0.2 Kelvin. Now let's make the difference in temperature is about 2 times 10 minus 16 Kelvin, so between system A and system B. And then again do the same calculation, log Wf over Wi. In this particular case will be 8 times 10 to the power 5. Still big. This is a 10 to the 6 is a million, so still big. And I repeat again until where you can see some smaller number. Delta T, delta T equals to, say, 2 times 10, oops, this is not minus 16, sorry. Let me erase that. Oops, it's not happening. Okay. This is minus 6, okay, not minus 16. So that gives you that number. So make it much smaller, minus 9, see, Kelvin. Then your log of Wf over Wi in this particular case will be 0.8. Okay, so in this case, this is the change of the number of states is quite small, so here one could actually see thermal fluctuations. And also you can have a feeling, okay, this is probably at this kind of minute or tiny kind of temperature differences, you'll find that things can fluctuate. That means things can also return back to the initial condition of the sorry, too much talking. Initial condition of the thermodynamical state. So things like your quasi-static processes can happen here. Okay. But so in other words, you need to have very small changes in your temperature to be able to see all these fluctuations process and possibly the reversible processes. Okay, so in this particular case, then you can return back to the initial temperature change at initial temperature condition. So that is the end of chapter 4 or chapter 4. So the next one will be chapter 5, which is talking about canonical ensemble. Well, let me just mention about the last section of this chapter 4. The last section of chapter 4 is something about the idea of Boltzmann being not accepted by the the community. So there are some stories you can read from there, but I'm not going to go through that. Okay, so you can read it up and see. So now I suppose one could also take a break at this point, I suppose. Should we do that? Okay, so we'll take a break of say 5 minutes. Okay, are you guys back? Okay, good. So I should probably start with the next chapter a little bit before we end, and I'll have some announcement to make later on. Please remind me that. So let's go back to the whiteboard. So I'm going to clear off all of this. So the next chapter is essentially on Canonicals Ensemble. But before we go to that, let's just explain the idea of a different ensemble that we have more or less touched on some of those of these things, but to make this a bit more defined in this particular context. So first we talk about ensemble of systems. Prepared to be identical in all senses. Identical, so all your systems are identical. And if it includes energy, including energy, for all systems, then this is sometimes called a micro-canonical ensemble. And in this micro-canonical ensemble, for example, everything is now of the same energy because you include energy in this identical property thing. So there your probability will be only limited in the sense of your particular quantum states. Probability of a system in particular quantum state that has that energy, quantum state, which is essentially given by the fraction ensemble in that state. So you still have this idea of statistical probability in that sense. Now, the idea of canonical ensemble essentially is to remove some of these constraints. Remember, our thermodynamical states can be thought of as systems. So, so one consider instead system prepared in the same way, identically, but allow energy transfer between systems so that energy in one system is not constant. Okay. So one can say identify one particular subsystem, identify sometimes I call it subsystems and sometimes I call system, but no, essentially you have a subsystem there in the whole ensemble. Okay, I should put a bracket, I suppose. I'm talking about system in ensemble, and then I talk about subsystem. It can be confusing. But the idea is, no, you look at those ensemble, you have systems which is prepared identically but can allow energy to be transferred between the systems. Okay, so identify one. Okay, identify a system there in the ensemble such that you consider other systems in thermal contact. Then this can be thought as a heat bath. Okay, such as, okay, maybe I should write from here. Such a system is called canonical ensemble. Okay. So if you consider the energy of this ensemble thing, so the combined system which is the identified system plus the heat path, then you expect that if this, okay, again, no, one has to put the condition combined system is thermally isolated. So that means the environment beyond all this ensemble will not be considered be participating in this heat exchange. So thermally isolated, then essentially the total energy is going to be constant. Okay. Also, one can talk about the entropy of the system. Which is given by this formula that you have seen before, but now this W is the number of accessible states in the combined system. So let's name the identified system to be system A. Okay, and then your total energy is given by the energy of the system A plus the rest, which I write as the heat bath here. So this is like your energy of heat bath or reservoir. So no, one can re-express, for example, UR to be just UT minus UA, and then you can see that later on we're going to use this. So the variable here, since this is constant with respect to the whole thing, okay, so the variable only will come from here. So the number of accessible states will be as follows. So it's W previously. So but now it depends on this energy of this system A. So this is like a variable here now. Okay, this will be given by the number of accessible states in system A plus, sorry, not plus, times, okay, because they are considered independent of each other, times your WR, the system of the states in the no, the heat bath, for example, and this is going to be dependent on UT minus U. Okay? So this will be states accessible to the heat bath. Let's take it stripped down to a simplest case that we can think of. Consider a quantum state psi I. So this is say going to be an energy eigenstate, for example. Quantum state psi I with energy EI from system A. So we specify that, okay, maybe I should say for rather than from, for system A, then I can write UA to be equals to EI, and WA, since there's only one particular quantum state, WA EI is going to be equals to 1. Okay. One should remember, how should I say, later on we'll talk about degenerate states. Okay, that means there will be quantum states, different quantum states that might have the same energy. At the moment we are considering, maybe I should write that down. This is non-degenerate. So once you have that, so the combined system now the number of accessible states to the whole system, to the combined system, is now given by, remember, is WAUA times WRUT minus UA. So I'm going to have WAUA is just going to be 1 times WR of UT minus EI. So in other words, the states of the combined system is going to be dependent on this accessible states of the heat bath. And the accessible states of the heat bath is going to be related to some particular temperature. So this is where things get a little bit interesting. So you have is given from our previous thermodynamic consideration is given by this derivative of the log WR with respect to the energy at constant volume. Okay, So that will be the temperature of the heat bath. And if by definition if you add heat to a heat bath, add energy to heat bath, there will be no change in temperature. Because the capacity of the heat bath is so much more, so there's no visible change. There will be no change in temperature. So now what one can do, so this is like a constant now, so I'm going to be able to say integrate star and that gives you WR equals to the, since there's a lot, I will have exponential here, UR on KBT. Gamma here is coming from constant or integration. But then, okay, plug this into here, so that's a star. So I put this as, say, triangle, okay, put back in triangle, then I will be able to associate the accessible states to the system with this particular energy given by gamma E ut minus EI, okay, because UR is just ut minus EI over KBT. Okay, so in other words, the heat bath sort of gives this temperature dependence to the number of accessible states for the system, the combined system. All right, what else do I need? Okay, if I consider all possible accessible states, total number, oops, sometimes it gets a delay there. Total number of accessible states, forgive my handwriting, then you sum over all possible states EI, and total will be sum over all possible EI. And if you do that, this gives you gamma EUT, KBT, and this will be a common factor out, and then sum J E minus EJ over KBT. So if you relate this to again to the relative frequency of this particular energy state, so then Pi equals to WEI divided by sum JWEJ. This gives you E minus EI on KBT divided by sum E minus EJ, sum over J, EJ on KBT. And this is essentially called the Boltzmann probability distribution. Now the denominator here has a name. The denominator is really like a normalizing factor, so that when you sum PIs, that will be just equals to 1 essentially. Okay, so the denominator itself plays an important role in a way of making sure that you have all these probabilities obey the unit sum. Okay, so the denominator is called, well, it's given the symbol Z. Oops, forgotten the sum. And this is called partition function. So most of the rest of this course will we look at this idea of partition function to define probabilities. Okay, what is Z really? Why is it called Z? This is from a German word, so you can read it up. I don't want to emphasize too much on that. So we'll look into the, okay, maybe before we finish, let's look at an example. So example here, okay, and again I emphasize non-degenerate states, energy states. So let's suppose I have 3 different energy levels. E1 equals 0, that's the ground state. E2 equals to something like 1.4 times 10 minus, better read that right, minus 23 joules. E3 equals to 2.8. So you can see that it's multiple of each other. Okay, and heat bath is at, say, at 2K. Then you can do some calculations there. Your partition function is given by e to the 0 plus e, remember it's minus ej on kbt, so that gives you this one is a multiple of kbt here, so that gives you e minus half. Please check with the figures. And then this one is e minus 1, and that gives you 1.9744. This is just a repeat of what's in the book. Okay, so the probability of each energy state can be calculated now to be the exponential of E1 over the Z given here. So this will be 0.506. P over E2 is 0.307. E3 is 0.186. So the idea here is, I think this should add up to 1. Well, almost, because there must be some errors of rounding off. But okay, the idea is one can start doing these types of calculations to with respect to a particular ensemble. Let me finish off with one last thing. So if there are degenerate states, so what does it mean by that? There exist different quantum states corresponding to the same energy. then the formula that we had before gets modified. Just write it down, then we can stop the lecture. So your partition function now becomes sum over the exponential again, but now you have this factor coming in. This is the degeneracy factor. So how many states are corresponding to the same energy? Okay. So that's all there is if you need to take into account degeneracies. So I will stop here today and probably will leave that as at this stage. We'll talk about more of this canonical ensemble after the semester break. Okay. Oh, the announcement. Okay, before I forget. The announcement, there is supposed to be a SCL module for you to do as a group. Okay, I believe you have done your assignments in pairs. So your SCL probably in groups of 4 kind of things. So that means you combine 2 pairs of students to be in a group and then try to do this SCL module. So what's inside this module is I'm going to give you some papers for you to read so that you can see the relevance of what you learned in the lectures in some of the scientific research. Okay, whether it's a historical paper, could be, or it could be a modern paper. Okay, so I will do that. Hopefully, if I have time, I will try to post this up on Putra Plus before the semester break. But if I can't, then I probably have to postpone this until after the break. Okay, so so I'll stop there for today. So let me take the attendance list. Come on. Okay, it's not happening. Yeah, okay. So that's it for today, and I hope you all enjoy your semester break. Okay, thank you everyone.